So we will discuss the memory related structures of the process descriptor, namely the task struct. So managing memory essentially is a key part of the real estate that a process owns, and a process owns a lot of memory throughout the memory map. So the memory map is, as we have discussed, it's a sparse structure. Most of the bottom part, well, I would say that the bottom half, it's not the bottom half, but the bottom portion, that part is populated. Then the top is populated with the stack. This is populated with the text and data and heap and so on. Then you have regions in the middle that are populated. These are for dynamically linked libraries, memory mapped files, and other things of a nature that are dynamically mapped into the memory space. And clearly the stack is downward growing, the heap is upward growing, and there is a massive void between them. So the memory map is indeed a very sparsely populated data structure. So the regions here, the virtual memory regions, someone has to keep track of them. What is it that I as a process I own, which is the job of the struct plus more. So we will see what all it contains. So the first thing, as I said, it contains a list or a data structure of regions of virtual memory. The nice thing with dividing the entire kind of disconnected virtual memory chunk, or let's say locally connected virtual memory chunks into these regions, is that it is possible to apply a standard set of policies for each region. For example, you can say that all the virtual pages in this region, you can only read but you cannot write to, or you can only read but you cannot execute. So a standard set of policies can be applied. A standard set of security policies, other restrictions can be applied. They can have a similar replacement policy. You can, for instance, say that these are very high priority pages. So these pages should be there. And in the worst case, if you are finding nothing else to evict, then only evict these pages, otherwise kindly keep them. So all of these policies and other attributes can be set at a region level, right? Virtual memory region level, which is why it makes sense to sort of keep track of what are all the contiguous regions within the memory map that a process owns. How to keep track of it, that is a several slide journey on its own. Keeping track of it is not very trivial, because essentially the data structure that we want to keep track of is something like this. If this is my memory map, then there is something, let's say here, then maybe another chunk here, maybe a tiny chunk here, then something here. And like that, you may have many chunks. So even if I were to answer a simple question, given a virtual address, can you say if it belongs to any chunk or not? Or if it belongs to a chunk, which chunk does it belong to? So maybe it belongs here, but the question is, how do you maintain the mapping? So this is not very trivial. And doing this in a high performance implementation, it is not very trivial at all. So we will see that doing this is reasonably involved. So we will use a structure called a maple tree to precisely store this information. This is the memory map. And within that, you have these contiguous zones, and storing them and effectively querying them, you will need a new kind or a different kind of data structure, which is a maple tree. So the maple tree will be discussed, and after that we will discuss other important features of the struct. So one is of course overall task size in terms of the number of pages that you own. So that's a trivial field. But another very important field is a pointer to the page table. So the entire multi-level page table with all its data and complexities and everything is represented just by a single pointer. That is how elegant the design is. That every task struct points to an struct, and struct points to a page table. And as I said, the page table is a huge structure, right? It's also a low-level structure because you support hardware walks. That said and done, a single pointer points to it. That's all. And it is of type called a page directory. So we will discuss what that is. Then you have a bunch of other statistics, number of VM regions, number of total pages, locked pages, pinned pages. So we need to again understand what is a locked page and what is a pinned page. So a locked page is something that you are seeing that kindly keep it in memory, do not evict it. So many such pages which are of important use, these are pages that you would like to keep and you would not like to displace. So they will have a very high priority, which means unless there is an absolute emergency, which means there are a lot of these high priority processes, or you just ended up blocking too many pages, the hardware will not evict them. It is a good idea to lock all the page table pages because you don't have a page table for a page table. So you sort of want to lock them in memory. And then there is called memory pinning. Pinning is not the same as locking. So pinning is an interesting thing. So the idea with pinning is like this. So let us say that this is my main memory. Let us say I have a frame here. The frame here was evicted. All right. So there was some virtual page that this was corresponding to. This one ended up being evicted. So it was sent to the swap space. Then later on there was a page fault. So this frame had to be brought back in. It may very well be brought back into time for a color change, a new location, and this mapping can be set here. This is very much possible. So pinning basically says this is not allowed. This basically means that if I am a virtual page, I am always mapped to the same frame. My mapping does not change. Again, pinning is a good idea for the page table because then you can deal directly in terms of the physical addresses, and especially in a large part of the kernel memory, the virtual and physical are the same, which basically means you are accessing physical memory directly. But since you will always go via the translation process, why not have a trivial translation where virtual and physical are the same? But this is possible only when you have pinning, because if it is displaced and then it is brought back to a different location, then there will be a problem. So that is why pinning maintains the mapping and locking maintains your presence in main memory. You can be locked as well as pinned, which basically means that your mapping is maintained and you are there. But the main thing is that if you are there, then your mapping is also maintained. So in a certain sense, what I said just now kind of trivially boils down to my second statement, that if no one is displacing you, your mapping will always be maintained. Only when you are getting displaced, then only the changed mapping makes sense. But broadly speaking, if you are an ultra high priority page like a page of a page table and you are not going to get displaced, then locking is good enough. But assume that there is some system emergency and some page table pages have to be thrown out. Then even if you are going to be read back in, it has to be at the same address. So that is why we have number of locked pages, number of pinned pages. And then some important memory regions, namely the code section, data section, stack section, their starting and ending virtual addresses are stored. So if this is the code section, then this part is stored. If this is the stack section, then this part is stored. So these virtual addresses are stored. Right? This is an important part of the memory map. So essentially, the job of the struct is to store the memory map, and whatever you are seeing is kind of in and around that, and have a pointer to the page table. Right? Broadly speaking, that is what this is doing. And then there is a pointer to the owner process, which means there is a back pointer to the task struct and the CPUs that this process has executed on. So this is an interesting data structure which requires a little bit of more explanation. So let us say that I have n CPUs. So I have 1 bit for each CPU. If the given task has executed on, let's say, CPU number 10, the 10th bit is set to 1. So let's assume this is 10th, and let's say it has not executed here, this is set to 0. So the key idea is that once a process is swapped out, let us assume that it is being brought in. If it is being brought in, which CPU should I choose? I will have a choice of many. I should ideally choose the one on which it was running the last time. Maybe that option is not available to me. If that option is not available, then I should choose one of the CPUs on which it has executed previously, right? In the recent past. This bitmap stores that information. And of course, in this bitmap, if let's say you executed long time back, the 1 can be converted to a 0. So far, so good. So what is the advantage of executing on a CPU on which you were previously executing? Cache locality. Caches are warm, its local TLB may be warm, right? So there is an advantage. So which is why this CPU bitmap is stored. So if I were to summarize the struct structure and why we need one. So it's not about Linux, but if I were to implement any OS, I would need something like this. The need for this is to basically keep track of the memory map, right? Keep track of all the virtual memory pages and have a pointer to the page table. And from a memory point of view, so here is a fun part. Why is CPU bitmap in struct? It could have been somewhere else. This is important because it is important from a memory point of view. That if I want to kind of maximize my cache hit rates, I need to find out on which CPUs I have executed in the recent past. And there also should be some algorithm of erasing the past. Because if I executed a long time ago, there's no point going there. It only has to be the recent. But there has to be some criterion for recency, which is why the CPU bitmap has been put here, such that all memory related information is in one place. So this is the big broad idea. So the question is that what does a virtual memory region or a contiguous region look like? So we have already said that this is our memory map. This is a VM region. So this VM region is represented by a VM area struct, which we will conveniently refer to as VMA, VM area. So every VM area has a VM start and a VM end, right? A start and an end. It's a contiguous region. Also, given the fact that every VMA is associated with an struct, we have a back pointer which we already have, which we always have. It's a circular relationship in the sense struct has multiple VMAs and every VMA points to the parent. So there is no rocket science here. We will discuss this in detail in the memory section, but let me broadly tell you what is anonymous memory and what is file backed memory. This is an important point, or this is an important concept, as you may call. So what happens is that if you consider all the memory regions, so let me maybe write them down. A stack, heap, then So this is a memory mapped file or a library. So what you see is that these are of a different nature, right? Their fundamental character is very different. The first is data and BSS are regions that are created at runtime, which means all the code that goes before the main function. Because the main function is the function at which you start, but that is not the point at which the CPU starts. So when you compile and link your C code, there is a lot of code that is executed, then it comes to your main, and your main may do a lot of work, and then again you do a lot, and finally you make the exit system call, right? That is the flow of a process. In this region, you actually initialize your your data and BSS section. If you have initialized variables, that is when you kind of load all the immediates into memory. So a program kind of auto loads itself. But the point is that these regions do not really grow and shrink in size. But the stack and heap grow and shrink in size depending upon the logic in the main. If you call more functions, your stack will grow. A recursive call, the stack will grow. Similarly, if you allocate more memory, your heap will grow. So this is completely runtime. So in a certain sense, after your program finishes, these areas are totally clear. But now if you look at this text and memory mapped files and so on, essentially here the real data is there in some file. And a file is basically a contiguous set of bytes on a storage device. So the real data is on a file. Part of that file is being mapped to the memory space of the process. For example, the file has all your program code, a part of that is being mapped to your virtual memory. Similarly, a file has some a huge library, it has a function. The code of that function is being mapped to your virtual memory. So essentially this part is file backed. Clear? Which means that for each of these memory regions, even if I were to clear it, I can again bring back the data from a file. But this part is totally program created. So it is said to be ephemeral, which basically means that it has a short life, as opposed to these regions which come from a file. So this part, which is kind of program created, has a short life, is known as an anonymous region because the program creates it. The data BSS part is also mostly anonymous because the program creates it, but in some cases, if it's already there in a file and then the entire thing is being lock, stock and barrel copied, then it becomes file backed, right? So let us not take a stand here. But if we look at the text section and memory mapped and so on, this part is file backed. So this broadly means that there are two kinds of pages in any OS. There are these anonymous regions which are created by the program, and then when the program finishes, they go. Then there are these file backed regions where basically a part of the file, the contiguous part of the file, gets reflected in the virtual memory space, right? So you'll only have these two kinds of pages. So anon pages and non-anon or file backed pages. Storing anonymous pages is a challenge. Okay, so this is something we will kind of realize the hard way, that storing that is a challenge. So you need a very elaborate data structure, which we will study in the section on memory. Not now, but we'll study there. So it does use a structure called anon VMA chain, but what is this complicated beast we'll look at later. In the other case of a file backed page, essentially you are a VM area region. So you know which file you are backing, which file is backing you. So you store a pointer to that file. So struct file is a pointer to a file, and you are storing a pointer to it, which basically means that I am not anonymous, I am file backed, and here is the file that is storing my backing data. So far so good. So now we will discuss something of fundamental importance called the maple tree. So the first thing is, this may be common knowledge to people from North America, But people from India, unless you have visited in a hill station, you may not have seen a maple leaf. So this is a maple leaf. It is Canada's national symbol. It's on their flag. And so on the maple, see, if you see, the maple leaf has a certain structure, right? It has a nice hierarchical structure. Also, it is not binary. So here, is it binary? It's not binary, right? So it's not binary. It has 5, right? Here again, 1, 2, 3, 4, 5, correct? So this is like nicely K-ary. So this is like nature inspiring science. So the maple tree inspires us to create a K-ary tree. Of course, this is slightly more complex than that. But broadly speaking, to answer the question that given a virtual address, which VMA am I a part of? That is what I want to answer. That given an address, given a virtual address, of course, which VMA am I a part of? A VMA is a contiguous region. As we have just seen, this is a VMA is a VM area struct, right? This is a VMA. So the question is, if I give you a virtual address, you tell me which VMA I am a part of, or tell me I'm not a part of anybody. For that, I will use a data structure called a maple tree. So now let us understand this tree business and work our way up. So in a typical undergraduate course on data structures, you study binary trees. So then you study binary search trees. So binary search trees are very good. If they are balanced, they give you order, log, and time complexity, and you can search for some item. So a binary search tree would look something like this, and you want it to be balanced. And there are variants of the traditional binary search tree which is actually balanced, like the red-black tree or the AVL tree, kind of complex algorithms, but they are balanced. So balance means that the height is order log n, which means the search process will take order log n. So that said and done, the red-black tree, which is binary, it's actually not a good idea. The reason it's not a good idea is because the entire world does not end with computational complexity. You have to look at the actual running time. The actual running time is essentially what matters, right? That is something that you care for. So given the fact that we need to be concerned with more practical issues, let us look at how you would actually do. So if you consider a 64-byte cache line, which is an atomic unit of storage in the caches, in the physical memory system broadly, can be 128 bytes, but you get the point. So what will happen in the case of binary? So in binary, what do you store? You store the pointer of the left child and the right child. So this information may just be here. What will you do with the rest of the cache line? You may store other nodes. So you may store another node here. Then you may store another node here, right? And then you may store another something here. So the key point is here. Yeah. So the key point is that if you want multiple threads to access this in parallel, right? So let's assume you're not writing, you're only reading. If you're reading, any data structure can be accessed in parallel. If that can be done, then what will happen is that maybe some core is accessing this part, some core is accessing this part. There will be a fair amount of fault sharing because you'll have occasional writes also. See, if you're only reading, then you can have your different copies, you can work on them, there's no issue. But there will be occasional writes. There'll be a lot of cache line bouncing. And also the other thing is, if you have binary, you'll have too many levels. So the moment it becomes a large structure, life becomes tough. This is why you actually have a multi-array tree the way that you saw a maple tree. So what you do is that you essentially store many children, as many as would fit in one cache line. So there is no chance of actually having disparate pieces of data, right, stored in the same cache line. Otherwise, I am accessing something and then this will become highly irregular. So there is no chance of this happening. Still, multiple cores can conflict on this. But then if they are conflicting on this, their addresses have to be similar. In other cases, even with dissimilar addresses, they were conflicting. And it is hence a better idea to sort of align the structure of my node with the size of a cache line. Alright, and have multiple children. If you have multiple children, they will also look the same, they will also have multiple, correct? So in this case, if you manage your data structure well and you have n nodes, you should require log n to the base m levels. You should require. Of course, within a level, so then this can act the same way as a binary search tree. So what you will do is that so I'll show you an example of what is called a B tree. So you could use hash tables also, but hash tables, the issue is it's hard to produce a sorted list of keys. It's hard to do a range query because hash tables break the ordering of the keys. Sometimes that is what I want. So a B tree looks like this. So let me quickly explain it, then I'll show you an example here, but let me at least make you go through this boring slide before we look at the more interesting slide. So in B tree of order m is something similar to what I showed. It is reasonably cache efficient. Every tree has at the most m children, not more than that. The root node has to contain one key. The root node has to contain a key. So essentially what happens is the root node contains this. If you are less than this key, you go here. If you are more than it, you go here. That's the idea. And let's say if you contain two keys, then clearly this is one key and this is one more key. You are less than this key, you go here. Between these two keys, you go here, right? And more than this key, you go here. So you kind of need to do a binary search within. So these are in sorted order, but you need to do a binary search within a node. So this takes log m time. That is why if you see the net asymptotic complexity is not very different actually. It is this multiplied with log of m, which basically becomes log of n. Alright, so in a certain sense, this is not like very fast. It's still the same, but again, as I said, you have fewer levels and then it's more cache efficient. So every internal node has to have ceiling of m by 2 children. So which means if you don't have this, how will you ensure that the depth is small? An internal node has to have ceiling of m by 2 children. Furthermore, if a node has k children, then you will have k minus 1 keys. That is obvious. You have 2 children, you have 1 key that is partitioning them. When you have k children, you will have k minus 1 partitions. Each partition is a key. Essentially, what you do is that you look at these keys. If you are less than this key, you go here. Between these two, go here. Between these two, go here. Greater than this, you go here. That is the big broad idea. So the issue now is that how do you find out where you are in which range? You do a binary search that takes log m time. And given the fact that you have log n to the base m levels, so it is this multiplied with this, which is log n. So this part is easily understood. And all the leaves are at the same level. Balanced tree. So broadly speaking, we are here that this is not a maple tree. This is a B tree, but we will go from B tree to a B plus tree to a maple tree. So we'll go stepwise. So this is a B tree where all the operations happen in log n time. Where this is something that we'll discuss. So what we see here is that we have a high level structure. The keys that it stores is 6 and 12. Anything less than 6 goes to the left. So here again the keys that you store are 2 and 4. Anything less than 2 is 1. Between 2 and 4 is 3. More than 4 but less than 6 is 5. So this part should be clear here. If you are between 6 and 12, you go here down. So all the key. So basically we again have two variants of this. If the keys can be stored in any node, it is a B tree. If the keys can be stored only at the leaves, it is a B plus tree. So a B plus tree in that sense is more disciplined, because 6 and 12 here, so in this case, you can have two kinds of keys. One key just plays the role of the separator. It may not actually be stored in the data structure, which means it will not be associated with a value. You can have another kind of key which is associated with a value, which kind of makes storage difficult, which is why a B plus tree is better. But broadly speaking, in a classical B tree, every key can be stored anywhere in the tree. So coming back, between 6 and 12 you go here. Then again two more keys, 8 and 10, less than 8, 7, between 8 and 10, 9, greater than 10 but less than 12 is 11. Finally greater than 12 go here, 16, 25. It's obvious why 14 should be here. It's greater than 12, it's less than 16. It's obvious why 17 should be here. It's greater than 12, between 16 and 25. And it's obvious why 26 should be here, because greater than 12, it's greater than 25. So broadly speaking, this is what a B tree is. Alright, so we are still not at a maple tree, but we are getting there. So we now understand what is a B tree. So the great advantage of this design, or this family of designs, is that every node we can store it in one or two contiguous cache lines, mostly in one cache line. That's the big idea. This means that your cache stores only your tree related information. It does not store other variables. For other variables, there could be a fair amount of writing and contention and so on, and that can cause fault sharing misses. And even let's say in this case, for instance, if the entire thing is stored in one cache line, someone could argue that multiple threads can try to access this. That part is correct, but they will still be accessing similar addresses. And when you're accessing similar addresses, there, you will be more open to the idea that there will be some conflicts and some slowdown. But in the case of a binary tree, if this is my cache line, I don't know who else are the occupants of the cache line, right? They could be other parts of the tree that, which you should allow other threads to access independently, but that will not happen. Or they could be other variables. So you don't have that kind of control. So that is why this is more cache efficient, and also you have fewer levels. But that is compensated for by the fact that you have to search within a level. So we're not getting a lot of advantage, but in terms of implementational simplicity and efficiency, that is where B trees have an advantage, which is why they are used in almost all storage systems such as databases and so on. So the guarantee is of course log n to the base m, and that is the heat, that is the height, and then you have insert, delete and search complexity of order of log n. And as we have discussed, a B plus tree, data is stored at the leaves. So a maple tree, what it does is that instead of storing a value, in the case of Linux, it stores a range, right? So it stores a range, which is a range between two numbers. So this can be like 14 to 16. So here instead of 16, it's actually 2. Instead of one number, it is two numbers, start and end. Ranges are compatible in the sense you say that, look, all of these are ranges. Ranges are not overlapping. If two ranges are not overlapping, you can clearly say one is greater than the other or one is less than the other. You just compare the lower of one with the higher of one, then you will figure out. So they store the ranges of these VMAs because two VMAs are never intersecting. Given the fact that they don't intersect, you can nicely arrange them in this fashion, and you can create a B plus tree. Furthermore, the branching factor is 10 for non-leaf nodes and 16 for leaf nodes. It is fixed. And for every node, it is 256 bytes, 4 cache lines. So the advantage of a B plus tree is, of course, that you don't have to store values or pointers to values in each node. So the structure of a node becomes more homogeneous. And here the branching factors are hardwired, as I said, 10 for non-leaf, 16 for leaf. And all the designs are made in such a way that the nodes of the tree nicely fit in cache line granularities. It does allow for more parallelism, because what will happen is that we minimize the chances of fault sharing. And if it's a large tree, then different threads can operate at different parts of it in parallel. So these are used to manage virtual memory regions. All right, so far so good. That this is the main or key advantage, that they are used to manage these virtual memory regions, and basically use a variant of a B plus tree to precisely do that. All right, so you won't have a minus hyphen here. It's just a B plus tree. So how would you insert and delete? Well, inserting and deleting is the same. You traverse the path, and then if, let's say, in any place you have a slot for another, in this case, if it's a B plus tree, of course something new has to be added. So you have to have an empty leaf in that region. You have to have somewhere in some region there is a leaf. So if you don't have it, then you'll have to split the parent. Correct. So the only option that remains over here is in the case of this, is that if, let's say, this is the parent, and assume that you are supposed to go here, and if this leaf is empty, you can nicely put the key here. But let's say if the entire parent is full, then what you have to do is you have to split it. But if you split it, now there will be two parents, right? One of this type, one more of this type, which means again one more key needs to be added at the top. So this is going to be a separator key, where basically less than it, you go here, greater than this, you go here, which means there has to be space in the grandparent. If you find that, you can kind of readjust things and create some space, that is good. If the grandparent is full, you'll have to split the grandparent. So keep doing this till you go up to the root. Finally, if you don't find space, you split the root. Similarly, for deletion, it is the reverse process. You get rid of the key, and we already have, this condition over here, that every internal node has to have ceiling of m by 2 children. If this is being violated, it is time to merge. In the first case, you split. In this case, you will merge. So those details are sort of taught better in a course on core data structures. But this is a broad idea of the maple tree in Linux, which is that it is a B plus tree with hardwired branching factors, which allows a lot of parallel access and cache line alignment, or fitting everything to a single cache line. This is observed religiously. So let us take a different look at the B tree. So the fundamental advantage is that it has fewer levels. So fewer levels will of course translate to a bigger advantage, especially when the B tree is stored on the hard disk, because the hard disk is a very slow medium. But the cache of course is much faster. Nevertheless, advantages exist. So if you could just consider a binary tree, something like this. So what can happen is that if each of these levels are stored on different cache lines, it will translate to many different cache accesses, right? Fetching those lines, ensuring that they are there in the highest level cache. But what happens in a B tree is that things are kind of packed. The main reason being that each entry only occupies a part of the cache line, not all of it. But what you can do in a B tree, for instance, is that you can completely pack a cache line. In fact, you can have several cache lines, but you can fully pack it. So what will happen is that you fetch a cache line, you have complete key information, So you know where you need to go because the cache line is the smallest atomic unit in the memory system. Then again, you fetch something, you know where to go. So if you look at it, you expect the number of cache fetches to be lower. And you also expect each cache block fetch to be more productive. In the sense that you will find more keys and pointers, everything nicely packed in one cache block. And that is not going to happen in the earlier case because you really don't know where these are stored. Are they stored on the same block, different blocks? That you don't know. And of course, the other advantage that is here is basically that if we have a cache block, in the case of a B tree, so a B tree basically ensures that all the residents of a cache line are part of the B tree and part of the same node. But in the case of a binary tree, you are not sure. This could be a resident of the cache line, but you don't know about the rest of the contents. The rest of the contents could be something that another core, for instance, accesses, and maybe it makes write accesses. So what will happen is this cache line will keep bouncing between cores, right? Between cores, it is just going to keep bouncing. So that is going to kill performance. But in this case, in the case of a B tree, that's not going to happen. You fetch something, you find all the pointers in there, and unless, of course, another core is trying to write to it, the chances of fault sharing are not there. If it's trying to write to it, it's like true sharing. Also, you can do node level locking. In case someone is trying to write to it, you can kind of lock the entire subtree by having maybe one additional field for a lock. So the entire subtree can easily be locked in this case, that you lock a node and you lock the subtree. And you can pack the lock also inside a cache line. So the advantages are numerous, which is why this has traditionally been used in databases, relational databases, everything. There, of course, we do more at the disk block level, right? Because in the disk, as I said, accesses are very, very slow. So there you see a big advantage. But here also the advantage is very clearly visible. And homogeneity and efficiency reasons would dictate that it is a much better idea to actually store the data at the leaves. All right, and the algorithms, as we discussed, are quite simple. That any search is a log n time operation. Any insert or delete. So insert basically would mean that I would like to find a free leaf. If I find a free leaf, well and good. Otherwise, free leaves have to be created. So it may be necessary to kind of split the parent node, right, and add it. So whenever there is a node, but you split it, then what happens is that you need to insert some sort of a separator at the top level node, such that one side points here and another side points here, right? One end points here, another end points to the other side. So far, so good. So similarly, deletion is the reverse process of merging. So let us look at this slide again that talks about the advantages and disadvantages of the B and B plus tree design. So the height is order log n to the base m. The search, insert, delete complexities are order of log n. And the B plus tree stores data at the leaves that we know. And you minimize fault sharing and node locking is possible. So we have just seen all of that. The maple tree is kind of an extension of this idea where the key is not one value, but it is rather two values. I'm only talking about the definition of the maple tree, not the general definition. My definition is the one that the kernel uses, right? So this needs to be borne in mind that this is not true of all possible maple trees, but let's focus on the specific maple tree that is used and implemented in the Linux kernel. So in this case, each key is a start-end tuple, and clearly the tuples are non-overlapping. So they are totally ordered in the sense that this represents an interval, start and end. Another tuple represents an interval, start and end. One is less than the other. All right. They are clearly comparable. And then what you can have is you can have a separator, but the separator can be a single value. right? So there's no harm in that. So given the fact that a key has a different definition, also the branching factor is kind of hardwired. So it's 10 for non-leaf nodes and 16 for leaf nodes. And it is, of course, faster than traditional red-black trees. And there are specific advantages for fitting everything inside a block, which makes the process efficient and minimizes fault sharing. So when you minimize fault sharing, you make it easy to actually engage with the maple tree in parallel, in the sense if you have multiple concurrent parallel threads, then they can in parallel read, write, modify parts of the maple tree. But of course, if kind of you're overlapping at the same subtree, then locking is required. But given that it is easy to lock in this case, that also is not that doesn't present a major challenge. So each virtual memory region is a tuple of start and end, starting point, ending point. So that is exactly what we are showing here. So the maple tree has kind of held us in good stead. So a second look at anonymous and non-anonymous. Non-anonymous is also file backed. Virtual memory. So as you have said, a virtual part of the virtual memory space can mirror an executable, that there is some part in the executable and all those bytes are read, placed in the memory image of the process and mapped to the virtual memory system. So what are those sections? The code section. The code section are all the instructions. They are there in the executable. We just copy them, put them in memory, map. Then the data section, which are the initialized global variables. So in that case also, all the initialization constants are there in your binary. Read it and copy paste in your address space, right? Which means you copy paste in main memory, but your virtual memory maps to those frames. And then shared libraries, that is a big advantage of having shared libraries, that if let's say 20 different programs are calling printf, I don't have to create 20 copies of the printf function. I have one copy of the printf function, all right, just one, and it is mapped to multiple processes. So far so good. In comparison, anonymous VM regions are things that are regions that are dynamically created during the execution of the program, such as the stack, the heap, and the BSS region, which are the uninitialized global variables. So all of these regions are dynamically created, so they are called anonymous, and then there are different ways, there should be different ways of managing them. Something that is file backed should be managed in a different way, because in many cases when you write something, the writes have to be sent back to the file. So our management strategy is different. But file backed regions will not grow and shrink, at least will not grow and shrink the way that anonymous regions will. So they have to be managed very differently. So there are different mechanisms. We will look at that. So now we have discussed broadly the memory related structures. So we will see that there are two pointers to structs kept, right? One is and active but this we will discuss later when we are discussing the context switch process, because actually both are required. But we don't want to open this topic now. But broadly speaking, what you should appreciate is the abstraction, which means that the rest of the world is not really concerned with how the memory system is implemented in an OS. They don't care. All that they care about is I have a struct called struct that is supposedly containing all the information, and I have a bunch of functions to deal with. Given that this is C, the functions are kind of kept outside in some file. Had it been C++ or Java or something, this would have been a nice class and those functions would have been inside the class. So that is one advantage of object orientation, but the overall concept is the same. The main concept here is of hiding. that I don't care how you implement your memory system, go ahead and implement it any way that you want. All right, and just give me a bunch of functions to work with it, and all I will send or receive is a pointer to this struct. That is all that I am concerned with. So this is a classic abstraction in computer science, where you deliberately do not care about the internal details. The internal details are not important to you, right? Insofar as the interface is kept intact, that is what you care about. All right, so basically in the next lecture we will discuss process IDs and the way that processes are managed. So we have been discussing different aspects of processes, but they were in the context of single processes, singletons. Now we will discuss how multiple processes are managed. So we will see that separate data structures are required to actually manage multiple processes.